I'll try to make that as, actually I've picked up another process example, which is not what I studied on, but which is what a former PhD student worked on, and at that time they had a different IP protection policy, so I can at least like give a bit of context.
Well, you said hydraulic, so it's got to raise curiosity now.
Yeah. I'll try to make that as.
What time is it?
5+2.
Are we okay on the 5-minute rule? Anyone expecting anyone else? So I'm really pleased to have everyone show up to this sort of unusually scheduled, if any of you haven't met before. Charles-Henri Clerget has recently come to ERL as a postdoc on the project with Equinor, which you might know is the new name for Statoil, that Pawan is also a postdoc in my group, and we're sort of about halfway through a 3-year project. Charles-Henri was a student at MINES ParisTech, and his research was supported by Total, and for that reason, some of what he'll present today is a little abstracted from the Total application, but I think it'll be very interesting. I had the pleasure of hearing Charles-Henri present this at Total's annual mathematical in France last year, and I think I'll be excited. So I hope you have a similar response to it. Please.
Okay. So good afternoon, everyone. I think I know almost everyone in the room, so most one or two, except one or two person. So my name is Charles-Henri Clerget. The work I'm going to be talking about is slightly different from what you're probably most of you used to it. I'll try to build as many bridges as possible with geoscience. So it's a problem. It's a control and dynamic optimization problem with applications in process system engineering. These are my co-author for this work. So Nicolas Petit was my PhD advisor back at MINES ParisTech, and Jean-Philippe Grimaldi and Myriam Chèvre are 2 people from Total. So Jean-Philippe has operational responsibilities in the advanced process control group at Total, and Myriam works with the R&D division. So basically, I'll be splitting this talk into 2 parts. First, an introduction, since I assume that most of you are not very familiar with control theory, so I'll try to give a bit of background on that, and what is this hydraulic delay problem that we're interested in. And then I'll be getting to the core of the problem, which is dynamic optimization under such hydraulic delay conditions. So first, a word about control theory. So the purpose of control theory is that given a system, so maybe a machine, maybe a chemical process, maybe a spacecraft, there can be many different applications. We're given actuators, which are devices which generate some signal that we can more or less freely choose. We have some measurements about some states of the system, and the question we're asking ourselves is, how can we impose a desired behavior to the system based on that? So in most common, like most standard control theory is based on the systems modeled dynamically through systems of differential equations, so this is going to be my choice of variable, like this notations are going to be standard during all the talk. I will come back on that a bit later. There is a bit of a clash with what you're used to, but for me, x is the state variable, so this is what describes the state of the system, and u is a control variable, so this is my leverage. This is my degree of freedom to make the system do what I want it to do. So this is the most standard formulation. There are actually extensions of control theory to system which are ruled by PDE equations. So that would be, for instance, wave equation. There is a lot of work on control of systems, hyperbolic PDE equation systems. Or DAE systems, differential algebraic equations, which are systems where some of the variables are related to the differential variables through static. So this is our Mamouzi. This is essentially an inverted pendulum, and this is a kind of system that we like a lot in control theory, because these are simple, unstable systems, which illustrates a lot, which have a pretty like rich enough behavior to begin with, and which actually are instrumental in studying some complicated problems, such as, for instance, biped walk. So on this video, which I must say come from ISR Stuttgart, they have built a system where you have an inverted pendulum. So each of this thing is linked to the other through a linkage which is not actuated, and this cart here is the only thing which is which we actually control. So we are trying to stabilize the system only by moving the cart. So obviously, if everything starts in a vertical way, then this is an equilibrium point, but it's very unstable. That is to say, as soon as we lose a perfect symmetry of the system, it's just the perturbation is going to go expanded, and it's just going to fall down. So here on this video, they are actually regulating it to force it to stabilize the position, and what you can see is that as soon as they turn off the controller, everything falls down because this is an unstable system. So this is the kind of thing we more generally try to achieve. Then another important question is, okay, we are able to regulate to a given set point, but can we, if we have exterior perturbation or some bias, can we actually correct them? So in this example, the researcher is like imposing a perturbation, and the system needs to fight against it to keep things stable, and slowly from this gets a bias and slowly comes back to its origin, correcting the bias. And as you can see, depending on like whether I'm hitting here, then it takes a lot of work to restabilize the system. If I kick here, it's a bit easier. Now, another kind of problem we are interested in is motion planning. So this is now the problem is, given a desired, not a set point, but a given desired trajectory that I'd like to impose onto the system, what is a control trajectory that will allow me to get that? Now this is a video from, actually from my lab, but 20 years ago, where they built this machine which basically inverts the dynamical equation of a robot actuated through 3 linkages, motorized linkages, and like puts the pendulum in upside position and keeps it stably there. So these are the main ingredients in control theory. We could also ask some more fundamental questions, such as, is the system commandable, is it observable, and so on, but I won't dive too much into this today. And just to make things a bit more like mathematically grounded, let's say, like the simplest example we could think of is if our system is a linear system, so which we usually write like this. So we have linear dynamics with respect to the state and with respect to the command. Then we try to come up with a linear feedback law. That is to say, the mapping from if the measurement I get from my system is here, what is the control action I must take to compensate for whatever discrepancy I will find between what I want to achieve and what is actually realized. And so when we plug that back into the dynamics equation, we get this, and so we can very easily see that this system with the linear feedback is stable if and only if this matrix has eigenvalues which have negative, and actually it's better, they are strictly negative real parts. Okay, now I think I don't have any movies, so I can stay here. So this was like the general setting. As I mentioned, control theory is used in many applications. The most notorious one are probably military application related to missile guidance, this kind of things, robotics, machine tools, and so on. And another major area of application is control and dynamic optimization of industrial processes. So in process industry, basically the rule of the game is that you are making commodities out of commodities. So your volumes are huge, your margins are tiny, 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 and so whatever tenth of a percent efficiency you can go scrap off will make you rich. So these are industries which have invested a lot and for a long time in control and optimization of their operations, and so it's an interesting playground for people in control theory. So this is a like view of the refinery where my operational advisor was located. So this is in the south of France, nearby Lyon. So it's a small to medium facility. That means it has tens of units and thousands of feedback loop. So it's a pretty complicated system, and a big challenge is to try to control and optimize a system like this, which has a lot of feedback loops within it, recycling streams, so a lot of interactions that you need to take into account. And now a word on delay. So as I mentioned earlier, my talk will be centered from the scientific standpoint on the control system submitted to some specific delays. The existence of delays, so when the ODE that is ruling the system is actually not an ODE, but rather differential, delay differential equation, is a pretty old problem in control theory because you actually find delays in a lot of settings. Could be computation delays if your controller is a bit slow, could be network communication lags, a lot of instances, and they have a very distinct, actually, have I? Oh no, okay. That's probably going to be better for everyone, I'm sorry about that. Delays have a very characteristic effect on dynamics of closed loop systems. So here I've plotted the closed loop evolution of a very simple system where I'm trying to track target value at 1. I have, in this case, what we call a low gain. So the gain is basically, to make it simple, the proportionality constant between what discrepancy I have on the variables I want to monitor and what, based on that, what action I take. So if I have an high gain for a small discrepancy, I take a big action, and the other way around. Now, as you can see, this is all right. This works fine, but this is a pretty lame control, actually, in the sense that it takes a lot of time to bring my system up there. And actually, if you were to look at the equation of the system, there is no really reason to go that slowly. But what I've not told you is that hidden in there is a small delay that I've not accounted for in my control scheme designer. And so if I actually try to get my gain larger, which is to drive my system to the desired reference value faster, then I get this. So this sort of spurious oscillatory behavior is very typical of systems with time delays when they are not compensated. And so basically the rule for practitioners is that when you have uncompensated time delays in your feedback loops, either you have to live with this kind of spurious oscillation, which we really don't like in process control, because then they go excite everywhere, like every other loops in the system, and everything starts to oscillate, and we really don't like that. Or you need to detune the gain, and that means you lose performance. So basically, all of your controllers are kind of lame, and you have to live with that. And like the stake in this talk is for a specific kind of delay that I'm going to detail now, like how can we come up with some solution when this delay is complicated to compensate it in our feedback. So, hydraulic delays. So basically what we are talking about today is pipes, essentially. So we have if you look at it from far enough, a refinery is essentially big tanks communicated through big pipes. And when the outlet of one of the tank is the inlet of the next one, this creates, if the pipe is big enough compared to the standard flow rates in the pipe, this leads to a transportation delay, which means that what leaves the first tank needs to take some time to go through the pipe and reach the second tank. And actually, if you look at it from a simplified perspective, that is, if you assume that this transport equation is purely a plugged flow model, so a vector equation, can't quite make it simpler, then you have actually an analytical solution. And in this case, strictly speaking, the action of this transport phenomena is purely time delay, whereas the delay is a bit complicated. It's defined implicitly through this integral relation. And this is what we want to be studying today. We are because this typically we do get in a lot of processing plants where we have recycling streams with variable recycling rates, or communication between the units which depend on the flow rate at the outlet of one unit. This flow rate is one of the control variables for the upstream unit, but it also affects this, let's say, communication delays with the downstream units.
Is that the equation that's solved, or I mean, is that the equation to be solved, or is it the equation? Is it a statement of how another equation is solved?
Let's say that it's one of the constraints on the problem that you want to solve.
Okay.
this will be made clear when I will have the full mathematical formulation, but basically the idea is that our equations are going to encompass some delays, and these delays will be defined through relations of this type.
Okay.
So before delving really into the process side of things, this kind of delays actually happens in other places. Another major application is in engine design, where typically you have, compared with the, let's say, speed of the reaction taking place, you have significant delays, for instance, between the combustion chambers and some downstreams, how should I say, sensors. And so basically you cannot properly control like automated injection. Lambda sensor is an oxygen sensor, by the way. You cannot control properly the combustion in this chamber if you don't take into account the fact that depending on the regime in which the engine is running, you will get a different transport lag. And an example more up to the point in terms of what Total wants to be doing, another example that could be given and which was studied by a former PhD student in my lab a couple of years ago, actually more than 10 years ago, it wasn't a couple now, is this. So this is a hydrodesulfuration process. So this is basically the process in which the oil refiner takes the sulfur out of the oil. So that's what prevents acid rains afterwards. And there are some very stringent regulations, whether in the US or France, about how much sulfur you can get in the commercial fuel that you sell and eventually burn. And this is a kind of unit that is going to help you to take that out of your fuel. So as you can see, it's pretty complicated. You have some recycling streams. You have different units which are, for instance, here the separator and the stripper, which are separated by a significant pipe. We don't measure everything at the same place. Some measurements are only done at the end, so after significant delays. So basically what is like typical in this architecture is that feeds, reactors, and analyzer are not collocated. That means that what happens at some point will affect later on after transport what happens somewhere else, and it might not be measured immediately. And also, so as I mentioned, you have cascade of reacting units, recycling streams, and so on. So now, more into the mathematical problem statement of this problem. So first off, so I mentioned that there are different ways to go about designing control policies, feedback loops. One of them, which is quite popular for some applications in nonlinear control, so basically what we would call hard control problems, is called optimal control problem. And I just want to pause a moment on this because I think this relates a lot to what you guys do, for instance, in full waveform inversion. So the way in this approach, in this paradigm, the way we want to come up with a control strategy is by solving an optimization problem. That is to say, we want to minimize over a certain time window a certain criteria which depend on the state and the control input. So usually this L, which I'm sorry doesn't mesh well with what L for you would, I guess, be the wave propagation operator. For me, I'm going to stick to the standard notation controls. This is going to be the cost function, but this is usually least square, so that should start to ring a bell. Then we have something that we have a dynamical constraint, which is given by the equation of the system. So for you, that would be the propagation of the wave. And you are trying to adjust a given parameter u, which for you, which in your notations would be the displacement field, but for me is going to be the control input. So essentially, sort of what we are doing is that this looks a lot like what you would be doing if you are trying to find M model vector, which is going to minimize some cost functions under dynamical constraints. Yeah?
But just a comment, the two equations fully define x. That's the...
Yeah, once u is given, the two equations fully define x.
Yeah.
So we have no, basically we do not touch into problems that are ill-posed. Basically, there's a whole theoretical field in control which is to study if problem systems are controllable and or observable, and basically if they are not, then we'll just say that's not for us to use. Your system is misdefined design, then you need to add more actuators or make the problem, maybe make your, for instance, what could happen is that if you have a simplified model, maybe it will look not commendable or not observable, but if you take into account more complex nonlinear effect, then it becomes so. But at least we'll go back to, okay, let's sit down again and design a better scheme. So we don't, our life is simpler in that sense. Now, the stationarity condition, so basically the condition that a candidate optimum solution of this problem has to verify is actually, like by design, very similar to what you do in FWI. So you are going to have one equation defining the forward model, what you call the forward model, we don't, but let's stick with that. Then you have an adjoint equation, which should be familiar to you, and then you have something to which we don't give a name, but which I would call a gradient term. This, you would see that if you do the scalar product of this thing with the perturbation of control, you would get the sensitivity of the cost, and so at optimum this thing has to be 0. So this is pretty similar, and actually I think this theory is what stemmed afterwards what is now used in a lot of data assimilation schemes or FWI, for instance. Now, specifically for my problem, what we want to be looking at is systems where possibly the dynamics is impacted by delayed value of the states and the command, where we have that this RU is defined as, yeah, that wasn't very smart of me, is defined through this relation where RU is equal to the current time minus the delay at this time, which is defined through an integral relation of the type of which I designed earlier. The only difference is that now we add, we take the action of a strictly positive function on the input to make things a bit more general. Yeah?
So, just like a high level question.
Yeah.
Whenever you talk about these time delays,
yeah,
the gut reflex is to Z transform, Laplace transform, Fourier transform, whatever. You take the Z transform or Laplace transform to account for the time delay.
Yeah. So yeah.
Why can't you do that here?
Because like it's only convenient to translate a time delay in the Laplace domain if the time delay is fixed. If it's fixed, then it's really easy. It's just a multiplication by a complex exponential, and then actually there's a lot of like pretty nice theory about that. You see that basically what we call the Nyquist diagram. I'm not quite sure to say that in English. Turns around, and you can see that when it crosses some points, then you become unstable and such. But for like a priori fixed but varying in time delays, and a fortiori for this kind of nonlinear problems, you can't apply that. So yeah, one thing which would anyway make Laplace transform not a good tool for this case, at least globally, is that this is actually a nonlinear relation. Because the input is acting bilinearly on the, like if you go back to not the delay but the advection equation it is a solution of, the input is acting bilinearly on the propagated field, let's say. But yeah, for fixed delay, what you just mentioned is basics of how we handle this kind of problems. That is true. Yeah, so, and actually most of what comes next, I will forget about this, because the system we were like mostly interested in for what Total was working on was a system where you don't have this and you only have a delayed input signal and the current input signal. Now, there are two most traditional ways to solve optimal control problems that are standard in the control literature. So one class of families is called indirect methods. So these are methods where you start by deriving the stationarity condition of the continuous system. That is to say, that is basically the stationarity condition that I exposed earlier, and then you try to solve them. So you can do it through, there are different ways to do it. You can do gradient descent in the functional space, or if you want to go to second order shooting methods, continuation methods, there are a whole bunch of them. It's pretty popular in control community for, I would say, 3 reasons. First, because it's elegant, which means that the math are dirty and complicated, and there's a lot of work to be done there. because they are known, and this is true, to yield very high accuracy, and also because they allow to handle some degenerate problems with singular arcs that I won't go into the detail of which I will not go today. However, when we started working on these problems, the stationarity conditions of this thing had not been investigated for input-dependent delays, so this was a new problem. And the other class of method are direct methods. So these are methods where instead of first deriving through functional analysis calculus of variation the stationary conditions and the gradient of the problem and then solving that numerically, you actually first discretize the minimization problem and try to solve it as a nonlinear program, and typically using orthogonal collocation methods. So this is the method which is usually preferred in process system engineering community. First, because contrary to indirect methods, which are very difficult to initialize, it is numerically very robust. It is very good at handling constraints, which is also something I will not dwell into detail, but which is difficult in indirect methods. So basically, in process control, usually any valve opening has to be between 0 and 1. Some temperatures are not allowed to go beyond the certain safety levels and so on. So this is important for us. And finally, it allows to leverage the very good existing nonlinear programming codes that are available. Now the problem is that when you try to do the discretization, and then again, in the interest of time, I won't go into the detail, but when you try to do the discretization of this problem with input-dependent delays, it finds out that it's numerically very impractical. It actually, interestingly enough, if the delay was variable in time, but in a way which is a priori fixed, then it's pretty straightforward to apply these methods to solve the problem, but with the input dependency, it becomes much more involved, and we did not really know how to do that. So this brings us to the steps we took to try to address the problem. So first, we wanted to characterize the solution of the problem. That means running basic calculus of variation for the problem with input-dependent delay, which have not been done before. So I won't go into the details, but essentially, and I think most of those who are working on FY are familiar with this, you define an extended cost function, which includes a Lagrange multiplier with the dynamical constraints, and basically you say that solving the finding candidate optimal solution, you necessarily have to satisfy these three Goto differential derivatives relations, which means that at an optimal solution, the first variation of the cost has to be stationary. And actually, when you do that, it's pretty technical, but you find out that actually the problem, as I have laid it down before, is actually non-Goto differentiable. So that's pretty bad, because that means the problem is not smooth. That means that basically any method, optimization method, which would be predicated on at least using the gradients, will fail, and that is pretty bad. And because these problems after discretization are big enough, we do not want to resort to non-smooth optimization methods. So this was actually surprising to us and a problem that we had to overcome. So the way we did that is actually not very complicated. I said, okay, let's just say that actually U, which is what we see as a control, is actually, let's make it a state variable, which is just the integral of an artificial control variable. And this is going to allow us to have a regularized control trajectories. And actually, when you do that, it turns out that this does yield a Goto differentiable formulation. So I don't want to hammer you with the mathematical formulation, just bear with me. So essentially, this, what I'm showing you now, looks a lot like what I've shown you before. In the first slide, which was linking to FYI stationarity conditions, you only have some additional terms because you have now these delay terms. So what is important is that this term here, which is specific to the fact that we have a delay, if we add a time varying but independent of the control delay, this term will still be here. But now, due to the regularization of the control, we have a second set of adjoint states, new. This blue term here is also the same as we would have if we had time varying but input independent delay. And these distributed terms here are the ones which are truly specific to this problem. And you can see this because if you remember, in the way we defined the delay function, it was defined by the implicit relation where 1 is equal to the integral between the delay time and the current time of phi of u. And so basically, if phi turns out to be something which is purely a function of time, which is independent of u, then this d phi with respect to du just vanishes, and you boil down to the time varying formulation without dependency. Yeah?
Just maybe another high-level question, just to get the intuition from what's happening. Is this strictly like a calculus of variations phenomenon? Is this strictly a calculus of variations? Just because in multivariable, if my function is not differentiable,
yeah,
and I add a strictly convex function to it, the sum does not magically become differentiable.
No, so basically the problem of differentiability comes, so I almost put them in, but then I thought it would be, actually, I mean later on if you want I can show you, or even in the question I can show you the derivation of the very simple functional of what's going on. And basically you see that because the problem is that when you, basically what happens when you perturb the control variable is that this implies a small change in the delay law. And basically what this means, what you would like to be able is that this small change is going to impact your dynamics by the fact that u of like delayed u is going to become delayed u plus the derivative of u at this point times like the variation of the delay. Does that make sense? Or
we can talk later.
Yeah, okay. But basically the problem is that the derivative, like what is important about this is that by introducing this term and this term, I make u a continuous function, actually differentiable function, and that is the situation where u is discontinuous, which raised the differentiability problem before that. And this quadratic term is actually just there to make sure that the problem is well defined. So that basically the problem is strictly convex with respect to v. The truly important stuff is this guy. Yeah, so basically, okay. So now we understand that the stationarity condition of this problem are not so different from those of a problem we wouldn't know how to solve, which would be varying delays, but varying in a way which does not depend on the input. And the additional terms, they just boil down to this. Okay. Now, this leads us to proposing an iterative resolution algorithm. So the main idea was at first, so this is a problem we'd like to solve now, because thanks to this regularization, this is well posed. This is well posed in the sense that it's smooth enough that we can apply the whole bunch of approaches we're used to. Now, would it be, but actually we don't know how to deal with this guy numerically. So would it be possible to solve a sequence of simpler auxiliary problems that we would know how to solve efficiently, which would eventually converge to what we want? So the first, the naive idea is to say, okay, we'll just do this. We'll create a sequence of problems where at every step we fix the value of the delay law based on what was the last value of the control input, and we'll just solve that iteratively, and hopefully we'll converge, and this will give us something meaningful. Now, this is really nice, because this guy, as I mentioned earlier, I know how to solve it using collocation methods, which are typically what I want to be solving because of the prerequisite of my problem. The problem is that actually this is wrong, precisely for the reason that I outlined before, because if we do this, then these terms, they always vanish. They're never taken into account. And so if you do converge to a solution, which actually is not clear, you know that necessarily it will be biased, because this will not be present in your stationarity condition. So this is, doing that looks nice, but it's actually not very smart. So instead what we proposed was this. So this is the same problem where I do fix the control, the delay law based on the last value of the control as a former step. But instead I add this sensitivity term, which actually, if you look at it, it exactly gives us a term that was lacking in the stationarity condition. So if this thing does converge, we will be having this term in our solution. So that's nice. That means that this solution will not be biased. And actually, if you think about it, you could show that this is sort of the first order, expansion of the cost function with respect to the sensitivity of the cost with respect to a change in the delay load. And this guy here is here for numerical convenience. So if you look at it, you'll see that once we converge, so Vn plus 1 and Vn asymptotically go to some V star, which is common, this just vanishes. And basically, this thing is just there to make sure that we are not going to move too fast. Now, the reason why we do that is because if your Un plus 1 gets too far from Un, then your linear approximation doesn't stand anymore. So you are doing garbage and you are not going to converge. This term here, by forcing us to not step too far at once, is going to enable us to actually converge. And if you're familiar with the trust region methods in optimization, this actually looks very much like the dual Sasha method. So this would be a method where you do nonlinear optimization by making a quadratic local approximation of your problem, but specifying that you have to stay within some realm, some radius from the point where you are currently are. And that allows you to make sure that your quadratic approximation is roughly correct, or at least good enough for what you are doing in this area, and then you move on. And now this is the same, but because in continuous framework it's annoying to have constraints, I just penalize it like this. But essentially, this is the very same idea. Okay, so actually, I won't go then again into the details to not go too much into technicalities, but we actually proved that this thing converge. And so the result is pretty technical, but the take-home message is pretty simple. It is that when alpha is very big, so when you only allow a very small step, then this all boils down to a gradient descent. So this, the technicalities are annoying, but the main idea is pretty simple. If you take alpha big enough, the linear approximation stands, and you will succeed. Now, okay, so a few words on two applications. So the first thing, yeah.
I just want to know, how do you choose how big alpha should be?
That's actually a tough question. So in this case, and that's a proof we made because basically we finalized this a couple of months before I defend my PhD. So then again, in the interest of time, I kept alpha constant. So the proof says, like the results say, at the end of the day, the theorem says that if alpha, there exists an alpha big enough under some smoothness conditions which are standard, there is an alpha big enough that this will work. Now this is interesting because it was not obvious from the beginning that the delay equations would be smooth enough that this would still be working. So we are happy about that. But this is not very practical indeed. So you have a couple of ways to deal with it. I've actually not been very far into like technical developments on how to choose it. So you could either try one alpha, which for whatever reason you like, and if it converges, then you're happy. If it doesn't converge, then you take it bigger because you know that eventually it's going to work. So that's not very good. Actually, I think the proper way to go about it, and the way I heuristically implement it in my actual solve, is to do the same thing as trust region method. So basically, you need a metric of what is the discrepancy between the cost reduction that you expected to get and what you actually get. And if this matches well enough, then you say that your local approximation is good, and you get alpha smaller. If it's not good enough, then you take it small. You take it smaller. Now, what is a bit tricky with that is in trust region method, you are used to using a quadratic approximation of the cost. So the problem is that if you, for instance, even though locally your linear approximation is very good, if you take alpha, which is 0, then this can always be made better by pushing UN plus 1 more in the direction towards which the gradient is pointing. So, so actually it's a bit more involved because you can never take that too hard because you still need to make the problem quadratic. Otherwise, it's a bit like an LP problem. In a linear programming problem, you know that if you don't have a constraint to stop you, you will go to infinity. And this is a bit what we get. So Practically, the way I did it is that I would check like what was the cost decrease. If the cost decrease is good enough, then lower it. If it's not good enough, increases it. But this actually calls for more developments. Okay. So now I'm just going to show you a few numerical examples to let you see what it looks like. So this is a very academic problem. This is interesting because it's an unstable second order oscillator. So basically what this means is that if we have been sloppy in our algorithms, this will blow up and we're never going to be able to catch the optimal solution. Practically the cost function that we try to minimize is this one. So this is basically saying that I want my state to be close to a given reference I'm giving to myself. So this would be, for instance, for you, this would be I want my observation to be close. I want my predicted state to be close to my actual observations. Then I want my control, what we call the control effort, to be not too far from a reference point. So this is actually a regularization term that we always have. So this would be a prior term for you. And this is, then again, this is the same thing, but on the pseudo, like the extra state that the extra control state that I introduced for the sake of regularity. And practically each of the intermediate problems that I mentioned earlier, we solve it using orthogonal collocation. It's coded in Ample, which is an algebraic modeling language, which is something which, for some reason I'm not yet sure of, doesn't seem to be used in FYI, but which is so convenient. So the Julia equivalent of this is jump. Basically, it's something that allows you to write a set of algebraic, write down your optimization problem, the algebraic constraints, and which will do all the automatic differentiation for you. And basically, after that, you can just plug it in on your solver, and that makes your life much, much, much easier. And actually, it's important because in this kind of method, we do need the Hessian. So we are going, the algorithm to solve the optimization problem work with the Hessian because we want a fast convergence. And our problem are not that big that we cannot afford to store it or compute it. So we really don't want to be doing this by hand all over the place. And IPOpt is a like state-of-the-art, large-scale constrained nonlinear optimization software, which is developed actually by a chemical engineering professor at Carnegie Mellon University. Okay, so this is a chart diagram. So first we initialize with some value for Vn. This allows you to get a Un straightforwardly by integrating. Then we compute for this values the delay law Rn. I've not talked about this, but basically if you go back to the stationarity condition, you would see that the reciprocal projection, basically the inverse of this function, is also used, so we need to compute it. Then we run one run of IPOpt to get the xn and the adjoint for this values based on the stationary condition. We compute the sensitivity term, and then we solve the next en plus 1 problem. Then we have some kind of termination criteria. If we're happy with what we've got, then we stop. Otherwise, we just plug it back in. And this is the kind of solution we get. So this is basically we are trying to steer a system from one equilibrium, which would be at 1, to another set point, which is here. So now it probably doesn't speak much, but this kind of like breaks here the trajectories. They are very unusual for finite order systems. So this, like this, probably looks a bit strange, but these guys here are interesting to see. So basically we're happy with that. We have managed to steer an unstable system to new set points, and that works well, and we're happy with that. So this shows you the way the value of the delay changes over this over the trajectory. So you have quite a bit, you have a substantial change because you have the amplitude of variation is of about like 35–40%. So this is a situation which would be pretty difficult to handle with standard control tools if you want good performances. So we're also happy with that. And this is just to illustrate to you the way the solution converges towards a solution. Like asymptotically converge. So U1 is initialization, so we just have a fixed state where we don't move from the initial coordinates. Then at 5 we are roughly getting the shape, but we are not quite there yet. 35 we're pretty good, and then we get into the problem that our approximation is first order approximation and not second order approximation, which means that the final convergence takes forever. So if you want to be really close to what would be like the best I can get for the optimal solution, which is a blue curve, you need 30 more iterations to get from here to this guy. So this is also like one of the drawbacks of what we did, which is that if you want the rough shape of the curve, then you get it quick enough. If you want it very fine, it takes longer. But this is expected from a first order method. Now the second problem, which is a problem we have communicated quite a bit on in our publications, which is somewhere in between a toy problem and what we might be interested in industrially, is what I call the paint problem. So you have 3 batch of paints here, here, here. So let's say this is, I never remember the primary colors, but this is blue, red, and yellow, maybe something like that. These two stuff here are pre-mixed here, and then goes through a pipe of given volume here, ends up at the outlet, folds into a big batch, and we have this color which arrives directly here. And this is because basically building a pipe is expensive and it takes a lot of space. So in a real plant we want basically to factorize as much as we can, and so you end up with very strange mixing and hydraulic structures where things get mixed ahead of time. And basically what we would like to be doing is at any given time control what is the composition in terms of these 2 colors of the outlet here. We could also want to control the integrated batch, but for today I just do the simulation on the instantaneous output because this is a bit more, I don't know, this is a bit more intuitive, I think. So the blanking dynamics are not too complicated, so you can relate basically the output to the inlet inputs through this relation, which basically is a matrix product where the term of this Gamma matrix are basically delayed ratio of the two first components. So this assumes that at this point we have instantaneous perfect mixing, which is never true, but which is actually a better assumption for what we do that one might expect. And then after that we have just plug flow, and here again perfect mixing. Then the delay is defined like this. So in this case, phi would be the sum of the first 2 components of the inlet vector, multiplied by f divided by vp to get 1 here. We fix the path to something, and also we want to impose, because we say basically that u1, u2, oh, there is a typo here. This should be u3, I'm sorry. These are ratios, so this whole thing has to be equal to 1. And this is the result. So what you would see here is basically, if you just forgot that there was a delay, then controlling this thing is not too hard, because basically what goes out is just what goes in. So if you want a given trajectory at the outlet, you just have to put exactly the same thing at the inlet, and you'll get what you want. That's if v pipe is equal to 0, there is no delay. Now that's basically this, given this dashed reference trajectory would like, this would just give this. So this is what I call the naive input, without giving yourself too much work. And this is what you actually get at the output of the system if you actually try to implement that, because actually you do have delays. So basically what you can see is that the transient is really very sloppy, and it takes forever. Basically you need to have converged to a new steady state so that you can actually hope that you are hitting the target. So this is really bad, and this is actually what is done most of the time. Then a first step toward making things better would be to say, okay, there is a delay, it's varying, but we don't know how to handle that. So let's just say it's a fixed delay. So let's take a reference value which will be computed based on the delay at the beginning of the time horizon, and let's optimize based on that. So this gives already a more complex solution. And here's what you get. So what you can see is that you have some missynchronization problem, like you have this big strange kick happening because at this point the delay has already changed, so you are making a big change here a bit ahead of time, so you have this kick at the beginning which we don't like too much. There is a bit of discrepancy afterwards, but it's already better. And then you have our method, where basically, so you can see the trajectory are more regular than here. This is because in these two cases, I didn't need to make any regularity assumption on the control, but now I have to be able to run my algorithm. And this looks like, this exact optimization looks like the fixed delay case, but not quite the same. And this actually, if you look at the output, this will allow you modulus the regularization of the inputs, which means that you can't have a discontinuity on the input. This will allow you to have perfect, basically, once you've flushed out the pipe, your system becomes controllable and you just hit the target. Okay, so that's about it. I've put here a couple, so I've not put a lot of bibliographies. This is just basically to give credit to the person I took some of the drawings and pictures from. Thank you for your time, and if you have any further question, we can go back to the dirty calculus of radiation if you like. If you have any other question, feel free to ask. Thank you.
Thank you, Charles-Henri. It was very interesting. Probably change of pace and content for all the people in the audience. I appreciate the questions. Who would like to ask more questions?
So will the noise in your measurements affect the delay? I mean, you have for a system, you have the output and you make the measurements, but the measurements should have some error or noise.
Yeah.
So have you considered the noise,
yeah.
the effects of noise?
So that's a good question. So basically, the standard way we deal with noise and only partially measured states in control theory is that on the one hand, we build what we call a controller, which is something that, assuming we measure the whole state, is going to tell you here is what the feedback you need to implement. And then we have a second part, which is what we call an observer, which either is there to basically filter out noise if you measure everything, or to reconstruct the state if you only measure some parts of it. And so in linear case, you can actually analytically prove that these two steps can be performed completely disjointly. So basically if you look at the spectrum of the whole of the matrix with the whole, like the actual state and the observed state, you'll see that it decomposes and the spectrum of the two parts are independent. So you can design one without the other, which actually in practice is not exactly true, but basically you can do one without the other. In nonlinear control, this is not so obvious, but we almost always make this assumption. And so in my case, in some other parts of my PhD, I had some things which actually run, and so we took care of that. But in this case, this was more about like assuming that everything is perfectly known, we don't know what to do. And so let's figure out the controller, and then when we need to run it online, basically what you would do is that you would, the standard, well, like, I mean, the lowest level way to handle with it, which is what almost everybody does, is actually put a low pass filter. That's more or less what you would do.
Thank you.
Yeah.
Are you able to characterize how much better your new control scheme is compared to the naive low gain controller? Like how nonlinear does the delay have to be for you to have a really big victory over the damage?
That's a difficult question. So anyway, because everything is nonlinear, it's very problem dependent.
Right. But just intuitively, do you have a guess?
So let's say what is sure is that if I show that to my boss at Total, this is really bad. This we don't want. Yeah. We are much happier with this. Wouldn't we be already happy with that? Unclear. There is, however, another problem which is difficult to quantify, but which we do know is there. Is that if you do this, okay, without going too much into details on like closed loop stability of systems with, because everything I've been talking about until now actually is motion planning. So you can use some scheme like MPC, things like that, where basically you do motion planning on a moving horizon, and basically at each new sampling time you reduce optimization, and this gives you a new action, and this gets you a closed loop policy. Basically, with these two cases, on top of not being perfect in terms of motion planning, what you would also get is that you would have not taken into account properly the delay, and in closed loop you would get back to this effect that I've shown you, where you would get spurious oscillation. Like, we know that in process engineering that's a big problem, because then again, if you start to have things which oscillate somewhere, because you have energy efficiency loops, so basically heat recycle, this kind of things everywhere, everything is very connected. Also you have recycling streams, so if things start to oscillate out of control somewhere, pretty quick, like quick enough, they do everywhere, and this becomes a nightmare because you can't isolate what thing is the source of what, and it's very, very difficult to troubleshoot. So we are very interested in suppressing this kind of behavior. I have some figures on like another work that we did. I know how much Total claims that they earn out of it. I'm not allowed to talk about it. And so people at Total think it's significant. Let's put it that way.
So I have a related question, which is, you mentioned the problem being the lack of Gateau differentiability.
Yep. So
for a PDE, how non-differentiable a solution is related to like a Sobolev space. If there's some parameter of non-differentiability, is there a similar way to measure how non-differentiable it is? It doesn't matter to your algorithm. Is it just discontinuous, or is almost?
Okay. So actually, I'm not so familiar. I mean, I've not done enough PD analysis, so what I can tell you is that is it here? Yes, here. Mm-hmm. So this problem, it's continuous, but it's not differentiable. If you just without the regularization. I don't know if that answers. I'm not sure that answers your question.
So
I wouldn't know.
Continuous could be this, or have a cusp.
No. Okay. So it's more going to be like. Okay. No, it's not going to explode. It's more like basically absolute. You are trying to optimize absolute value. Okay. Except that you have this this differentiability everywhere, and so it's annoying.
Was there another question? Yeah.
So in the iterative algorithm,
yeah,
you have when you obtain V and plus 1, you need to solve another optimization problem.
Okay.
So is that you exactly solve the problem?
So can you repeat your question again, please?
Yeah. So here.
Yeah.
So when you compute the V n plus 1, you minimize over V n plus 1. Right? So
Yes.
Do you solve this problem exactly, or?
So the question is, do I do just a gradient step on this, or do I solve this thing completely?
Yeah.
So the way we did it, that's also a good question. The way we did it is we actually solve this to optimality and then move on. It's not clear it's the smartest way to go about it. It may not be worse, like going through the pain of actually solving things. The reason why it still made sense. The reason why it still made sense for us is because, the bottom line is I'm not sure it's the best way to do it. For us, it worked well, probably because most of the nonlinearity was lurking in the delay rather than something else. But it's not obvious that it's what you should do. You could just try to solve this, do the first step, and then move on. So one of the nice things, let's say, from an implementation point of view of running this way, is that I get to use IPOpt as a black box, and I don't need. I mean, you could you could specify some you could specify a number of iterations to get the cuts quick enough, but then because it's an interior point method, you would get sloppy constraint management. So it's, let's say it's expedient to do it like this, and for what we did, it was good enough. If you, out of the blue, it's not clear that you should solve this to optimality and then move on. Actually, it's much more likely that you should only solve enough of it that it's that the linear approximation is good, and then redo the approximation and move on.
Any other questions? I have a very basic question I wanted to ask first, but the other questions are more interesting. Basically, for people in this room who are mostly thinking of geophysics or oil and gas applications, without revealing why Total had you do this, can you list maybe 3 relevant applications? None of which need be yours, but just
so this type of delays is very typical of process problems. So basically, it's really you have a pipe and you have something flowing through the pipe. And
like the paint model is.
Yeah, the paint model. The engine problem is actually a real world problem. There have been patents on that. Former PhD students. Let me move on. This one.
Okay.
Yeah, because basically what happens is that you have a lag between the measurement and basically you're trying to measure here what the way the combustion took place in the chamber. And depending on the regime you are in, the inlet flow rate is different, and so this will affect a lot the lag here. So if you are at low regime, the lag becomes pretty big, and actually if you don't take that into account in the design of your controller, you're not able to do a clean automatic injection. So this is pretty important.
What about in the natural world? Because there's usually not a control system. Control systems have to do with machines.
Yes.
Usually. So does this kind of analysis or description apply to natural phenomena at all, or only things that were there's some artifice and some intention?
I mean, so to some extent, but in a much more complicated way. So like inverting the wave equation looks a lot like that, because basically you are looking, instead of being like, so basically I'm looking for the speed of the advection equation, which will give me what I want, or which at least, given the other things I need to do, will not perturb what I'm doing. And what you are doing when you're inverting it, when you're inverting the wave equation, is that you are also trying to fit the speed, but of an equation which is not an advection equation, which is a more complex hyperbolic equation. So in this sense, you could, like, I've actually been thinking a bit about this recently.
Think of the speed as a control input?
In my case?
No, in the wave.
Well, in what you do in FYI is that you are trying to find a field of velocity, which plays sort of the role of speed, that will fit your measurements. So basically, the field of velocity is your control variable in my language. It's actually a bit improper to say that, but let's stick to that for now. And you're trying to adjust it so that instead of bringing the state where you want it to be, you're trying to match your observations with what you have actually seen.
Okay.
So I mean, but my case is in a sense much simpler because the wave equation is super simple. It's just an advection equation. It's not a wave. I mean, it's an advection equation. It's not a wave equation.
Yeah.
Then like more actually, so this kind of problem. So I know that my PhD advisor is talking to some people of Statoil or now Equinor about some like regulation of the mud. Like, without going too much into detail, they don't get allowed to talk about. But basically, you inject mud during the drilling process, and this mud is recirculated and pretty much you get exactly the same kind of dynamics.
Right.
Where like what you are doing at some point, and depending on the flow rate at which you are doing, is impacting at which speed things circle back. I think it's more, to be honest, it's more of a machine-oriented problem, in the sense that this advection equation is a very simplified representation of some transport processes. So actually, also in engine engineering, the place where it's used is to model some distributed system. Like for instance, when you are trying to capture pollutant particles on a catalyst bed at the outlet of the car, you can also. So this is the state basically of the catalyst is a PDE, but it has been shown that you can actually capture it pretty well with a reduced order model that uses this kind of blood flow with variable speed approximation. So basically, if you want to go to something more complex than purely what was done for, there are some instances where you can try to use it to basically build a reduced order model of a more complicated distributed equation. Yeah.
Great.
I'd say that.
Any other last questions?
Yeah.
Very simple question. So, can you explain a little bit about your final result? Why one result is better than
so you are talking about the paint problem?
Yeah. Just
okay. So I don't know how well you see from where you stand actually. Okay. So basically, these dashed lines are, yeah, this is terrible. I'm sorry about that. These dashed lines are the output trajectories you'd like to do. So basically, you are trying to do so we would call it in process engineering a grade transition. So you are working at one set point where for a long time everything was running at these levels, and you want to move it to something else. And basically, you want the transient to be not too sloppy. That's your goal. Now, if you do what I call the naive control strategy, then you get this, and what you see is that like the red should be on this dashed green line, and the green line is here, and the red does that. And same thing, the blue is very off. The yellow is not off because this one is directly plugged into the output, and there is no pre-blend on this one. But the two others are really bad, and they stay bad for a long time. So basically, that means that if you are implementing that in open loop in a plant, you are not controlling anything about what's going on between two steady states. So basically, when, like for instance, this was the input you needed to produce, I don't know, like a chemical, let's say, and these are the market condition is changing. Your boss changes mind, anything. You need to change the chemical you are producing. That means changing the inlet ratio, the ratios of the different components in the blend. Now, if you do this, that means that everything which happens between these 2 points here is essentially crap. So this is completely off spec, and you're not going to be able to sell it. Possibly you have to recycle it into the plant because you can't afford to just dump it. So you lose basically you have wasted your time here. You are wasting, at best you have wasted your time, at worst you have wasted your time and product. If you do this, then you're much closer. So instead of reaching more or less what you want here, you do it around here, which is a bit earlier. And in the meantime, in this part, you are off, but you are less off. And in this case, you are just at the target from here. So it's all about not wasting time. Basically, as much as when you run a big chemical plant, you want it to run continuous. So basically, you want to start it up one day and then have it run forever at the same conditions. And if you are producing ammonia, for instance, that's fine, because essentially your inputs are always the same, your output is always the same, it's ammonia. And as much as you can, you just run it for 10 years without touching anything, and that makes everyone's life much easier. Now, one of the problems when you do refining is that your input is changing, because basically depending on what is the last cargo of crude oil you got, this completely changes the components that you have in the barrel, and this completely changes the economics of the refinery. You need to change all the set points, and also because there are many different kind of final product that you could be selling. You could be doing naphtha, kerosene, gasoline, diesel, light fuels, heavy fuels, coke. I mean, there are a lot of things that you could be doing, and depending on the price of energy utilities, on the spot price of the product, it's not clear which one you should be doing. So you have to, I mean, you earn a lot of money if you are able to have flexibility along your production chain, and usually being able to deal with transient in a nice way is an important element to achieve that.
Great. All right, so I'm going to exert the privilege to cut off the questions for now. Thanks for everyone for bringing your questions. And Charles-Henri sits in what number?
213, I think.
213 sounds right. If you have any more questions, I'll be happy to answer them at length.
Yeah.
Thanks again.